Hello, space fans, and welcome back to G Fun Facts Online, the show that dives deep into the most mind-blowing corners of our universe. Today, we're venturing out to the icy realms of the outer solar system to talk about something truly spectacular: volcanoes that erupt ice. That's right, not molten rock, but super chilled water, ammonia, or methane. It's called cryovolcanism, and it's not just a cool, pun intended, geological quirk. It's shaping entire worlds and could even point us towards life beyond Earth. So grab your thermal gear, because we're about to explore these icy giants. First up, what exactly is cryovolcanism? Imagine a volcano, but instead of glowing red lava, it spews out a mixture of volatiles, things like water, ammonia, or methane. These substances are liquid deep inside some of Jupiter's icy moons, like Europa and Ganymede, but they flash freeze into ice and frost when they hit the incredibly cold surface. It's a dramatic process that sculpts the landscapes of these distant worlds. So, what's powering these frigid eruptions? The main culprit is something called tidal heating. Picture Jupiter, this colossal planet, with its immense gravitational pull. Now add its moons, tugging at each other as they orbit. For moons like Europa and Ganymede, this constant gravitational flexing from Jupiter and neighboring moons literally squeezes and stretches their interiors. This creates a massive amount of internal friction, which generates heat. Enough heat, in fact, to melt subsurface ice and form vast oceans hidden beneath miles-thick icy crusts. Think of it like repeatedly bending a metal spoon. It gets warm, right? Same principle, but on a planetary scale. This effect is especially strong for moons in what's called an orbital resonance, like Europa, which orbits Jupiter twice for every one orbit of its volcanic neighbor, Io. The closer the moon is to Jupiter, the more eccentric its orbit, the more Jupiter's gravity yanks it around, the hotter it gets inside. But tidal heating isn't the only player. The internal composition of these moons is also key. If you've ever put salt on an icy road, you know it lowers the freezing point of water. Well, these moons aren't pure water ice. They contain substances like ammonia or various salts, which act like natural antifreeze. This makes it much easier for those subsurface oceans to form and stay liquid, even in the frigid depths of the outer solar system. These oceans then become the source for the cryomagma, or ice lava. Under pressure, this liquid can be forced up through cracks and fissures in the moon's icy shell, leading to an eruption. The thickness and makeup of this icy crust then dictates how and how often these eruptions occur. Interestingly, some scientists think that not all cryovolcanic eruptions tap into these deep global oceans. On a moon like Europa, for example, eruptions might instead come from pockets of salty water or brine that are trapped within the icy shell itself. These brine pockets can move around within the ice, driven by temperature differences, and become more concentrated. If these pockets eventually freeze, the expanding ice can create immense pressure, leading to explosive eruptions that blast water vapor and ice particles far out into space. Okay, so this all sounds pretty wild, but how do we actually know cryovolcanism is happening? We have some compelling evidence. Take Europa. Its surface shows these jumbled, blocky landscapes called chaos terrain, alongside smooth plains. Scientists believe these features are formed when subsurface water or slush wells up and erupts. And get this, the Hubble Space Telescope has even spotted hints of giant plumes of water vapor erupting from Europa, potentially shooting hundreds of kilometers high. Then there's Ganymede, Jupiter's largest moon. It has vast areas of grooved terrain and bright, smooth regions, like one called Arbella Sulcus, which look like the aftermath of ancient cryovolcanic flows. Now it's important to distinguish this from Io, Jupiter's other famous moon. Io is the most volcanically active body in our solar system, but its volcanoes spew molten rock due to even more intense tidal heating. That's regular volcanism, not cryovolcanism. And the exciting part? We're on the cusp of learning so much more. NASA's Europa Clipper mission is set to arrive at Jupiter in 2030, and ESA's JUICE mission, the Jupiter Icy Moons Explorer, is already on its way. with a special focus on Ganymede, expected to arrive around 2031. Europa Clipper is designed to make multiple flybys of Europa, and might even be able to fly directly through any active plumes, sampling their composition. Imagine what we could learn from that. Now, this is where it gets really interesting for anyone wondering about life beyond Earth. Cryovolcanism is a huge deal for astrobiologists. Why? Because it creates a direct link between potentially habitable, subsurface liquid water environments and the surface. Think about it. The first key ingredient for life as we know it is liquid water. These subsurface oceans, shielded from harsh surface radiation by thick ice shells, could offer stable environments where life might arise or persist. Cryovolcanism then acts like a cosmic elevator, transporting materials and energy. It could bring vital chemical nutrients up from the moon's rocky interior, or from the ocean floor, perhaps from hydrothermal vents similar to those found in Earth's deep oceans. These vents, if they exist on icy moons, could provide the heat and chemical building blocks necessary for microbial communities to thrive, just like they do on Earth. And here's the kicker. If life does exist in these subsurface oceans, cryovolcanic plumes could carry evidence of it, what we call biosignatures, to the surface or even into space. This means spacecraft could potentially detect signs of life by flying through these plumes, without the incredibly difficult task of drilling through miles of ice. It's like getting a free sample of an alien ocean. The discovery of active cryovolcanism and these hidden oceans totally redefines what we consider the habitable zone around a star. It shows that habitable environments don't just depend on sunlight. They can exist far from a star's warmth, powered by internal heat sources like tidal forces. Even if some plumes originate from those shallower brine pockets within the ice shell, rather than the deep ocean, studying them still gives us incredible insights into the moon's chemistry and the processes that could support life. Exploring these icy worlds and their cryovolcanic activity is crucial. It helps us understand the potential for life to pop up in the most extreme environments, and broadens our whole perspective on where life might be found in the universe. So as future missions like Europa Clipper and JUICE prepare to give us our closest look yet at these frozen frontiers, we stand on the verge of potentially revolutionary discoveries. Cryovolcanism isn't just a geological marvel, it's a beacon guiding us in the search for life beyond Earth. That's all the time we have for today on G Fun Facts Online. I hope you're as excited as I am about these icy, erupting worlds. Join us next time for more fascinating facts from around the cosmos. Don't forget to subscribe and keep looking up.